Okay, I've got a couple of equilibrium problems that I want to do to close out chapter 15. Here's one where we got zero point 0.5 molar of hydrogen iodide. So we're going to make this our ice table, ICE. And this is 0.500 molar. And they also give me 0.100 and 0.100 for the iodide. So we've got hydrogen and iodide. So for everything in this reaction, I've got a concentration. And the deal is that if I'm looking at this little diagram that I use, I don't know where I am on this diagram. I don't know if I'm where Q is less than K and the reaction has to go forward. I don't know if I'm Q greater than K, so the reaction has to run in reverse. And I definitely don't know if I'm at equilibrium. I suspect not, or we wouldn't have a problem to solve. And you know what happens at equilibrium. The reaction rate in both directions is the same. Rate forward equals rate reverse. So we need to calculate Q. So the equilibrium constant expression for Q, the Q expression is the same as the equilibrium constant expression. This will be H2 times I2 divided by HI. And notice that HI has a coefficient of 2, so we have to square that. All right, so we're just going to go ahead and calculate Q here. The concentration of H2 is 0.100, and the concentration of I2 is the same, it's 0.100. And then the concentration down here for HI is 0.500, and we have to square that term. So we'll go ahead and put that in the calculator. So that's just going to be 0.100 squared divided by 0.5 squared, which gives us 0.04. So Q is equal to 0.0400. Now, let's compare it to K. K is over here, and K is 0.0200. So if I'm going to compare Q to K, K is 0.0200, and Q is 0.0400. I think you can see that Q is larger than K, so I'm over here on this side of the reaction, on this side of the equilibrium where Q is greater than K, and so to get to equilibrium, the reaction has to run in reverse. It actually has to go in this direction. And so when I do my change here, the minus X is actually going to be on the product side. And then the plus X, and this will be plus 2X, is going to be on the reactant side because the reaction is running in reverse. And then I do what I normally do, which is simply add the initial to the change line. So this is 0.500 plus 2X. This is 0.1 minus X, so 0.100 minus X, and 0.100 minus X. Okay, now that I've got that, and I'm encouraging you to always write the equilibrium constant expression, which is going to be H2 I2 divided by HI, and we're going to square that. Okay, so here we go. Okay, let's plug everything in. We've got 0.0200, which is my equilibrium constant. For my numerator, that for H2 and I2, that'll be 0.100 minus X times 0.100 minus X, which is just 0.100 minus X squared. And then for my denominator, I've got 0.500 plus 2x, and again I have to square that. Well, this is a perfect square algebraically, and so we can get rid of the square by simply taking the square root of both sides. So let's go ahead and do that. First thing I'm going to do is take the square root of 0.02. So I'll plug that in the calculator, and that gives me 0.1414. So I've got 0.1414, and then that will be equal to 0.100 minus x, and then divided by 0.500 plus 2x. Now, all I'm going to do now is I'm going to move the 0.5 plus 2x to the other side by multiplying 0.500 plus 2x times both sides. It will go away here. I'm going to rewrite things down here, so this will be 0.1414 times 0.500 plus 2x is equal to 0.100 minus x. I'm going to distribute the 0.1414 inside the parentheses. So let's see, times 0.5, that gives me 0.0707. So now I've got 0.0707 and then plus 0.2828x is equal to 0.100 minus x. All I did was take my 0.1414, multiplied it times 0.5, gave me 0.0707 times 2x, which gave me plus 0.2828x. Now I'm going to just combine my terms. I'm going to go ahead and move the x's over to the left and move the 0.0707 over to the right. So I'll subtract 0.0707 from both sides. So this is going to be minus 0.0707. I'm going to add x to both sides, and this is a 1x. So this is plus 1x. So what is that going to give me? Let's move up here where I have a little bit of room. So 1x plus 0.2828 x gives me 1.2828x, and then 0.1 minus 0.0707, so that's 0.1 minus that, and that gives me, looks like 0.0293. So I now have 0.0293. I'm going to go ahead, solve for x by dividing both sides by 1.2828, and that goes away there, and 1.2828, and that'll give me a value for x. X will be equal to, let's see, 0.0293 divided by 1.2828, which gives me 0.0228. So x is 0.0228 molar, or atmospheres, whatever the unit of concentration has to be. Now, x is not my concentration. Remember, what I have to do is I have to subtract it from 0.1 to get my H2 concentration at equilibrium, and I have to add 2x to 0.5 to get my HI concentration at equilibrium. So my H2 concentration, which will equal my I2 concentration, will be equal to 0.100 minus x, which is 0.0228 And let's see what that gets. 0.1 minus that. And that gives me, looks like 0.0772. So here I've got 0.0772 molar. All right. And then finally, let's go ahead and get the HI concentration. That's going to be 0.500 plus 2x, which is 2 times 0.0228. And let's do that. 0.5 plus 2 times 0.0228. And that gives me, looks like 0.546. So I have 0.546 molar at equilibrium for my HI concentration. Now I can test that, I can check to make sure I've gotten it right by simply looking at the equilibrium constant expression, plug in those equilibrium concentrations and see if I get K, which is 0.02. So let's do that. For H2 and I2, I have 0.0772 times 0.0772, so I'm going to square that, and then I'm going to divide that by 0.546. I have to square that because of the coefficient of 2 for hydrogen iodide, so let's do that. So we've got 0.0772 squared divided by 0.546 squared, and I get 0.0, this is what I got, 0.01999, which will definitely, to 3 sig figs, go ahead and round to 0.0200. Okay, that's my check, and so I think I've got good answers there for everything. This is my X value. Okay, let's move on to another problem that I think you'll find useful. The thrust of this problem was I had to calculate Q to determine which way the reaction would go. That occurs when you have non-zero concentrations for all the components of the reaction. Okay, I did a problem in class where you actually had to use the quadratic formula to solve a quadratic equation. Now, that may come up from time to time, but I actually don't want to give that kind of a problem to you on an exam because I think it just takes too long, and it's essentially an algebra problem, and what I'm interested in are chemistry problems. So here's a case where you have a small k, a small equilibrium constant, and you have a large concentration of reactant. So let's go ahead and work this problem where we have a small equilibrium constant. This is 10 to the minus 4. The concentration that I'm given for this problem for my reactant is 0.5 molar concentration, or 0.5 atmospheres. And what you need to remember is this 0.5 molar or 0.5 atmospheres is a large concentration with respect to this tiny 10 to the minus 4 equilibrium constant. Now, if you remember, if you have small equilibrium constants, much less than 1, they are reactant favored. So at equilibrium, this problem is going to be mostly reactant. I'm going to have some products, but I'm not going to have a lot of products at equilibrium, all right? And so when you have a small equilibrium constant, I'm going to go ahead and give you a rule, and that is your equilibrium constant is 1,000 times less than your reactant concentration, okay? And when you do that, well, let me just go ahead and show you how this is going to work. Okay, so I've got my initial concentration. I don't have any products here. My change here is going to be minus x, because my coefficient is 1, plus x over here, and plus x over here. At equilibrium, I'm just going to add my initial to my change. That'll be 0.500 minus x. 0 plus x is x, and 0 plus x is x. Let's go ahead and write the equilibrium constant expression over here. So that's going to be K is equal to carbon monoxide, CO, times Cl2 gas. Nasty reaction, by the way. Don't want to breathe this in at all. And divided by this stuff right here. Okay. All right. So now I've got my reaction, and I'm going to take a look at something. Now, my equilibrium constant is 8.34 times 10 to the minus 4, and that will equal x times x, which is just x squared. Now, if I were to divide by 0.5 minus x, if I were to do 0.500 minus x, that is going to give me a quadratic equation, and I would have to solve it with the quadratic formula. In order to avoid that, in this very special circumstance, I'm going to make an assumption that the x with respect to this starting concentration is small. And so I'm going to go ahead and ignore it and test later. All right, and I'll show you what you've got to test for. You just want it to be small enough to ignore. So if I do that, I'm going to go ahead, instead of dividing by 0.5 minus x and getting a quadratic, I'm going to do this. 8.34 times 10 to the minus 4 is equal to x squared divided by 0.500. Now that is a much easier problem. We'll multiply both sides by 0.500. It'll cancel over here. I'll do the same thing over here, 0.500. We're going to multiply it times 8.34. Let's see what we get. So that's going to be 0.5 times 8.34 times 10 to the minus 4, and I get 4.17 times 10 to the minus 4 is equal to x squared. All I have to do to solve for x is take the square root. And so I'll do that, and that gives me an x value of 0.0204. So x is equal to 0.0204 molar or atmospheres, depending on what the unit of concentration is. Now, how do I see if that is an acceptable thing to do to ignore the x with respect to the starting concentration? Well, I test it. I test it by determining what percent my x value is with respect to the starting concentration. So I've got 0.0204 divided by the starting concentration, which is 0.500, and then I multiply by 100. So I'll divide that by 0.500 and then multiply times 100, and I get 4.1%. So that's 4.1%. As long as the percent of x divided by whatever your starting concentration is, your reactant concentration, as long as it is less than 5%, you are okay to ignore this X. It is small enough to simply ignore it. Okay? You can do the quadratic, and I've done this problem with the quadratic, and you get a better answer in the hundredths place. Or actually not in the hundredths place, in the thousandths place. So, and it's just a tiny, tiny bit. So this is, as long as it's less than 5% of your starting concentration, you are good to go. All right, that's it for this video.